To end this chapter, we will look at an application of this theorem of Menger other than the application to matchings. So we will look at not Menger's theorem for vertices, but Menger's theorem for edges. And we want to do a similar thing for directed graphs. So I will not show you why this is true, but there is a theorem, a directed version of Menger, that says that the maximum number of arc disjoint paths from a vertex V to a vertex W in a digraph is equal to the minimum number of arcs in a VW disconnecting set. So now we have here V, here we have W. The situation looks the same somehow, except now our edges are directed. So we can have something like that. And we're looking at directed edges and directed paths from V to W. So I'll leave it to you to check or to believe me that you can generalize or alter the notions that we dealt with before so that they apply to digraphs. Why do we want to do this? We'll apply this to network flows. What is a network? So before saying what a network is, our idea is that you have, say, a network of channels, maybe water channels or electricity channels, and you want to measure the limiting capacity of this network. So how many liters of water can I pump through this network of channels without at any moment exceeding the capacity of every part of the channel. Maybe at some place I have a bottleneck and then I cannot exceed that quantity. Apart from electricity and water distribution, this has an application to product delivery if you're delivering products along a certain delivery chain, or epidemic spread for that matter. If you have a person who's infected and then you have all sorts of ways to infect another person. And so in such a problem, your interest would be to cut this flow in as an efficient way as possible in order to stop the epidemic spread. To model this graph theoretically by a network, we just mean a weighted digraph, and the weight of an arc is called the capacity of the arc. So let's look at this very simple example. So suppose I have this digraph with two edges E1 and E2, say with capacity 3 or 5. So maybe this means that in the first channel I can send 3 liters of water per minute. In the second I can send 5 liters of water per minute. So I can replace this, if you wish, by some... So instead of drawing this, I could just as well have drawn 8 directed edges altogether, 8 arcs, and somehow to not have this weight. So I replace my edge weighted 3, my channel that takes 3 liters per minute, with 3 channels that take 1 liter per minute. But it's more convenient to use weighted digraphs. And philosophically, as I've hinted, the capacity measures the maximum quantity that can flow through each arc. So if you have a network, there are some vertices with no inflow, just all the arcs going out from that source, out from that vertex, and that such a vertex is called a source. And a sink if there is nothing flowing out from this vertex, meaning that all the edges are directed into this vertex. And you commonly assume that there is exactly one source and exactly one sink. And we're interested in flows from V to W. So we have V here and W here. And maybe you have some such path. Let's say like that. And you have, well, let's say 8, 5, 6. So for this to make sense in applications, you want the weights to be non-negative. And now I've mentioned the word flow multiple times. What is a flow? So in a network, in a weighted digraph, a flow is a function that assigns to each arc a real number greater than or equal to 0, satisfying two conditions. This number cannot be more than the capacity of the arc, and at each vertex, apart from the source and the sink, we assume that we have exactly one source and one sink. So apart from the source and the sink, at each vertex, the flow along arcs into U equals the flow along arcs out from U. So this is exactly the situation where you would have, so let's look at this simple example, where you have water flowing. So if I have the capacity of this arc is equal to 3 and the capacity of this arc is equal to 2. So if I want to send water from V to A, maybe I can send here, instead I can send 1.5 liters per minute, and then of course it will continue to be 1.5 liters per minute because I cannot have water amassing here at the middle vertex. And also at no point can my flow send more water than the channel can actually take. So this is what makes sense of the first condition. Philosophically, again, this is water flowing without exceeding channel capacity. And now if you have, say, a pandemic flow and a pandemic spread and you want to stop it, or if you have a water flow and you want to think about what happens if there is some accident that cuts channels. So a cut is a set of arcs so that each path from the source to the sink contains an arc in this cut. Meaning that if I remove the arcs in a cut, or if I shut the channels in the arc, then water cannot flow at all from the source to the sink. And it is possible to show that the directed version of Menger's theorem from a minute ago is equivalent to this catchily named Maxflow mincut theorem. Namely, the value of any maximum flow is equal to the capacity of any minimum cut. So if I have, say, something like this, here V, here W, and say this is 5, this is 3, this is 6, 1, 4. I might want to ask, what is the maximum amount of water, if these are channels, and these are capacities in liters per minute, how much water can I maximally pump from V to W? Well, you look at all the cuts, and what is a minimum cut? Well, the least possible, so in this graph, any cut has to have one edge from upstairs and one edge from downstairs. And the ones with smallest value is these 3 and 1. So this means that the maximum flow will have 4 liters per minute, because that is the size of the cut. So the cut measures somehow the size of a bottleneck. And this is one way of applying Menger's theorem. So Menger's theorems, the vertex version had applications to matchings, and Hall's theorem followed from it. So now we have 2 proofs of Hall's theorem. And the edge version had a directed version that is equivalent to this Maxflow min-cut theorem, which is a much more intuitive way of phrasing it. Just a word about the proof. So the idea of the proof is that if all your arc capacities are integers, then you can replace an arc with capacity k by k arcs. Now you have an unweighted directed graph, and you can apply the directed Menger to that graph. If your capacities are not integers, remember they were non-negative real numbers, then approximate them with rational numbers and remove the denominators. And you can make the approximations so good that the approximation itself doesn't alter the proof, the truth of the theorem. So this is just to give you an idea how Menger's theorem is related to this Maxflow mincut theorem.